Welcome to Comfort-Calc. We're putting together a residential steam seminar. We're going to start off with some basics and boiler sizing. The basics will be uh, just different information about steam and about the steam system, and then a quick uh, piece on boiler sizing. There's going to be a total of 12 videos. The first one we're going to put on YouTube, and the rest of them you have to get on our website, which is comfort-calc.com. Comfort-calc.com. So this is part one of 12 parts. So let's see what we have to offer. The first central heating system was a steam system about 1841. Now we're talking about a central heating system, meaning that it was throughout the entire building. The first heating system claimed to be installed in the United States was at Eastern State Penitentiary in Philadelphia, Pennsylvania. I read since then that some people argue it might be the White House. Immaterial, 1841 was the first central heating system. It was only pipes. If you go into the doorway of this entrance of the Eastern State Penitentiary, you'll see these pipes on the wall. There was no radiators back then. Actually, the radiation went from pipes to steel radiators to cast iron radiators, but they were just pipes. If you go into the big entrance where they would bring prisoners in, in the paddy wagons, as they called them, you would see these pipes on the walls. They operated approximately 60 psi. Now today that's a lot different, but back then the steam pressure was running about 60 psi, which is dangerous, as we all know. Between 1879 and 1891, steam boiler explosions killed 3,123 people and injured 4,352 people. So combine these together, in that time period, there were 7,475 people injured or killed that was actually reported. There was probably some that weren't reported. In 1880, they adopted the 2 psi rule residentially, which still stands today on residential applications. You use 2 psi back then or you don't get paid. So they were pretty straightforward with this whole idea of going to 2 psi and saving lives. So if we look at steam itself, it's being produced in the boiler, and 1 pound of water will produce 25 cubic feet of steam. So that's approximately 1,500 times as it expands out into steam into a vapor. So let's assume that we have 1 cup of steam. We would actually end up with about 1,500 cups of steam. So it doesn't take a lot of water in the boiler to heat a building with steam. And steam actually, you'll see, moves very rapidly. Talk about steam pressure. Residentially, you don't require a lot of steam pressure. Some companies operate in ounces of pressure, some operate in pounds of pressure. Almost any, and I say almost because there's a lot of variations of steam systems, but the majority of the steam systems, we could operate in ounces and it would still work good. I always say the best steam system is one that never builds pressure, but it'll still heat the building. The biggest enemy of steam pressures and steam systems is the pressure itself. The higher we raise that pressure, the more problems we're going to encounter. And we'll take a look at those a little bit later in the seminar. I talk about heating a building with steam heat without talking about latent heat. That's the heat required to convert a liquid to a vapor. It's not going to change the temperature. We're going to take 212 degree water and produce 212 degree steam. We have to add another 970 BTUs per pound of water to accomplish this, making that transaction from liquid to vapor. This sounds like it could be pretty expensive because that's 5 times the energy it took to change water from 32 degrees to 212 degrees. So let's recap that. If we have 32 degree water, not ice, but just 32 degree water, and we're going to convert it to 212, all those BTUs it takes to raise that water temperature from 32 to 212, it's 5 times that much to convert it to to a vapor. Now, we're not raising the water temperature from 32 to 212 in the system, so it's a little misleading there. That's just a comparison. We're taking that water at room temperature on the first cycle or two and raising it to 212. But then as the boiler cycles off, that water coming back is about 180. So then we're going to convert it from that point to 212. So we're changing that 5 times number. That's just as a comparison to see where we are. So we've added 970 BTUs per pound of water. We converted to steam. Now we're going to get a lot of those BTUs back from converting it to latent heat, because when we get out in the system, to have that steam condense, we got to remove those 970 BTUs per pound of water. We're going to put it into the iron of the radiation, and then it's going to radiate out. So we're gaining almost all that back. We're only looking at the change from whatever the water temperature is in the boiler to 212. And then once we hit that 212 water, we're converting it by adding the 970, but then the 970 is coming back out in the system. So we're not really losing a lot at that point. Greater steam pressure equals higher steam temperatures to a point, but you'd have to really add a lot of pressure to make a difference. We're not changing the latent heat part of it. We're only changing the amount of pressure in the system. We're compressing the steam more to raise the pressure. Steam's not heating the radiation, the latent heat is. So to add all this steam pressure doesn't do anything more than just cost a whole lot of money. The rate of steam pressure change is exponential. So if you're looking at creating steam at 1 pound of pressure and then you change it to 2 pounds, that's an exponential growth to making it from 0 to 1 pound. And if you go from 2 pounds to 3 pounds, that's another exponential growth. It's not an equal growth just going from pound to pound to pound. Many steam systems have way too much steam pressure on them, and way too much could be 3 pounds or 4 pounds of system pressure. We should really think about heating at lower pressures, maybe even ounces of pressure instead of pounds of pressure. That would be beneficial. Latent heat is what heats the building. Let's talk about air removal. We have to get the air out of the system to allow steam to rise. And probably one of the more overlooked items on a steam system are the vents. I have seen many one-pipe steam systems. There's supposed to be a vent somewhere down the line on the main line, and there's a plug in it. The vent was removed probably because it was leaking and not replaced. That just starts running the fuel bills higher. We have to vent that air. We have to get that steam to the end of the main as quickly as we can on a one-pipe system, and then start venting the radiation. So we want to move that steam out quickly from the boiler. All steam systems need to vent air to move the steam faster. We can't just compress the air because it's not venting fast enough. That starts building pressure, and again, of course, we know that pressure costs more money to operate at. At zero pressure, steam moves through an insulated pipe at approximately 30 to 50 feet a second. So we're saying zero pressure in the system yet, a little bit in the boiler maybe, but it's an insulated main, so it's not going to condense as rapidly once we get that pickup factor where we're heating the pipe up. And then we're going to move that steam quickly through the system. We start building pressure, then the steam slows down. At 5 psi, the steam would move through the pipe about 22 feet per second. Now that may seem odd because at zero we're moving faster than we are at 5 psi. Remember, it's not an open-ended pipe. We have to compress the steam. So as we start building more pressure and starting to compress that steam, we have to run longer to make that happen. If it was just an open-ended pipe, it'd be hard to get to 5 psi maybe, but it would move out the end pretty quick. But this is a closed system. Steam boilers are rated in terms of square feet of steam. It's called EDR, equivalent direct radiation. It's the original term for square feet of radiation. Briefly mentioned EDR in the last slide. Let's talk a little bit about that. So that's the effective heating surface of a radiator. Uh, it, they go by square feet of radiation. Each square foot of radiation, or EDR, equals 240 BTUs at 1 psi. So if you do get 1 psi, you will be getting 240 BTUs for every square foot of radiation in that structure. To convert EDR, square foot of radiation, to BTUs, you multiply that times 240. So that means the total number of square foot of radiation times 240 will actually give you the BTUs. Now, just the opposite, if you convert from BTUs to square feet of radiation, that means you're going to take the BTUs and divide them by the EDR, square foot of radiation. You're going to divide that by 240. So that'll give you the total square foot EDR that boiler will put out. High pressure goes to low pressure always. That's physics. You can't change that. So high pressure will always go to low pressure. Remember, the high pressure is in the boiler. It's always going to be higher than what's in the system when the boiler is running. And the longer the boiler runs and the pressure increases in the boiler, the pressure in the system will increase. It doesn't matter if it's ounces of pressure or pounds of pressure, but high pressure will always go to low pressure. Things to consider when you're replacing a steam boiler, and we're just going to highlight a couple of them here. Of course, all the steam boilers need to be resized and installed the proper size, which means you have to check the radiation count and see what's there, and then size the boiler off the square feet of radiation that would be required for the building. Plan on replacing all the near boiler piping. It may or may not be right, but some things might have changed a little bit through time. But I would always consider repiping the near boiler piping from and to the supply pipes. It probably wouldn't be a bad idea to consider replacing maybe 10 feet of a wet return if it's there, because that last 10 feet before the boiler always seems to get fairly corroded up. Always record the old boiler water level. When you install the new boiler, it's good to try and get that water close to where the old level was. This is just in case there's some hidden stuff that you don't see, like whatever connections were wet before should be wet again. And with the new boilers being shorter and a lower water level, that could create dry connections that were wet, and then you could have steam issues and heating issues and other things that happen there. If the boiler's in a pit, you can either leave it in the pit or double check your A or B dimensions, and we talk about that in a different part of this seminar. And if it's going to interfere with your A or B dimensions, then leave it in the pit. If you can bring it out of the pit and install the proper A dimension or B dimension, then you're okay. There's another thing called a false water line, which we will get to another part in the seminar, which you can get from our website. If it's equipped with a condensate receiver or boiler feed tank, make note of their piping and location before removing or replacing. Some of these systems, when we get into system types, again, in a different part of the seminar, some of these, the measurements are very critical. Other ones, they're not. But we will discuss that later. But a lot of people just leave the same pump in there if there's one there. We always prefer today with these smaller boilers a boiler feed tank instead of a condensate pump. And of course, that's in another part of the seminar. Pipe the boiler per the boiler specification with minimal deviation. There are reasons to closely follow the directions. Years ago, the boilers were larger and they had what they call a steam chest, which is from the water level to the top of the boiler. And that was a disengaging, the steam was disengaging at the water level and getting a little dry as it traveled up through the steam chest and then went up into the piping and dried out some more. Today, that steam chest is gone. There's very, very little steam chest in today's boilers. So the near boiler piping that the manufacturer shows is actually part of the steam chest. It helps dry the steam. By code, the manufacturers must meet 98% dry steam. And to do that, they have to include the piping because the boiler doesn't have a good steam chest anymore. So it's got to be piped per the manufacturer's directions. Check the pitch of the steam mains and returns. Make sure they're going in the right direction. Hangers come loose, buildings settle, um, pipes will droop. So we got to make sure that everything's proper and we're not going to trap water anywhere. If you drop a hanger and the pipe's going to have a little belly in it there, it's going to trap water and you're going to get a bunch of noise. So just make sure all the hangers are there and maybe get levels and put levels on the pipes every so often to make sure that they're all running the right direction. We're talking about system piping here, not so much boiler piping. And check or replace the mainline steam vents. One pipe systems, you're always going to have a mainline steam vent. Two pipe systems, you're going to have traps and other ways of venting. But radiators, you have radiator vents on one pipe steam systems. Normally two pipe steam systems won't have radiator vents because they're going to vent through a pipe somewhere. So this is all kind of guidelines on replacing a new steam boiler. Talk about sizing the boiler. You have to check each and every radiator. What that means is you have to measure the radiator. You got to measure the height. How tall does the radiator stand? It goes from the floor, which includes the legs. It goes from the floor up, not from where the bottom of the radiator actually is, excluding legs. You got to go from the floor all the way to the top of the radiator. Now it'll give you your height. The next thing you're looking for is the number of tubes or columns. Every radiator will have one or two pipes going into it. So from the pipe end, doesn't matter which end, but from the pipe end, let's say, you have one or two or three columns or one or two, three tubes in that radiator. So we're looking at one section, how many vertical tubes or columns are there? Then you would write that down. And then the last thing is how many sections that make up the length of the radiator. So we're going to go from, let's say, all the way to the left, all the way to right, looking face on the radiator. This is going to give you the total length. Some people like to measure the length. The number of sections is more accurate. So if we have the height, the number of columns or tubes, and we'll talk about the differences there, and the number of sections, that's what you need to properly size a steam boiler. Then when you convert all this to square feet of radiation, that's when you choose a boiler size. And again, BTUs doesn't really matter when it comes to steam. Steam ratings are 33% greater than what's listed in the literature. This is called a pickup factor. So it takes so many BTUs to heat the piping. And they add extra radiation for that, or extra boiler BTUs to heat up the piping. Once all the piping's hot, that actually converts over to usable BTUs for heating and or usable steam for heating. So there is a little bit of extra in there, and that's always good to remember. Look at this radiation. These are called column type radiators. The columns are pretty wide. You can see at the end where the little pipes would go in the bottom there. But this is a column style radiator. And then the number of sections is which would go from the front right there to the back. That you would count the number of sections there. And then you have these charts, and this is how you determine how many square feet of radiation you have. You have height in inches down the left column, and then you have one column, two column, three column, four column, or five column radiators. This is actually showing each one of those is actually a three column. So you find your height, you go across that row until you come to the number of columns, and there's a number in there. And let's say that it's a 23-inch radiator and it's two columns, your multiplier is 2.33. Then you take that 2.33 times the number of sections. So it's down the left column, get your height, and then go across the row until you get the number of columns. That's your multiplier. Multiply that times the number of sections, and that radiator is X number of square feet. We'll have an example in a little bit. So that's pretty easy to figure that out. Let's look at an example. This is a column type radiator again, same one. It's 32 inches high. It's 3 columns. So our multiplier then would be 4.5, and that radiator is 19 sections long. So it's 4.5 times 19. And then that's going to give you that radiator is 85.5 square feet of radiation. That's one. And then you can go ahead and do all of them and just total them up. And then go to your color brochure and pick a boiler off the square foot of radiation. Now here's a little tip that speeds things up a little bit. Let's say you have 5 radiators that are 32 inches tall. So if you have all 5 radiators at 32 inches, and the total number of sections for all 5 comes to 50, you would take 4.5 times 50. You don't have to do each one independently, although it's not bad to do that sometimes, but most cases, I would always just take, okay, all my radiators 23 inches tall, my radiators 32 inches, whatever they are, count the number of sections as long as they're the same type radiator, like a column type or tube type. So again, these are column type radiators. So let's say we have the 3 column radiator at 10 sections. We're just going to walk through an example here if you're going to do each one. 32 inches tall. And so it'd be 4.5 times 10 sections. So the chart told us that 3 column, 32 inches was 4.5. 4.5 times 10 is 45 square feet. And then the next radiator is only 2 columns, but it's 24 sections, 32 inches. Do the math, that comes out to 79.2. And we'll just follow that the whole way down. And let's say there's only 4 radiators in this house. Kind of unusual, but it's just an example. So these 4 radiators come out to 339.2 total square feet of radiation. So that's how we would size our boiler. Now, here's a little note. It says if mains are not insulated, that's the main around the basement, where the radiation pipes come off and go up to up to the radiators. If that main pipe around the basement, it has to be insulated. If it's not, it becomes a radiator, and you have to measure that out and you have to add that in. And that's where some people fail because they don't think of the piping. They just think of the radiation. And the piping up to the radiators, we don't really have to count, but the main pipe has to be insulated. Has to be insulated. And if not, it becomes a radiator. You got to count it, add it in. Count it and add it in. Let's say we have a job here with non-insulated mains. And here's our criteria. We have 150 feet of 2-inch pipe. We have 40 feet of 1.5-inch pipe, and we have 30 feet of 1-inch pipe. So on this chart, it tells us what the BTUs are. So we're going to calculate this out. 150 feet will be 31,800 BTUs. And then we go to the 40 foot of 1.5-inch pipe and the 30 feet of 1-inch pipe. And we're going to have a total of 42,410 BTUs. So that's our total length of a non-insulated main. Now we got to convert that to square feet of radiation. So we do the math for that. 42,412 divided by 240, that's the BTUs in square foot of radiation at 1 psi, comes out to 176 square feet of steam. Now we have to add that to our calculation, which we'll do in the next slide. So it takes us back to where we were. We add the 176 square feet, and now we have 515 square feet of steam. Remember, if the mains are uninsulated, insulate them. Don't let it run without insulation on those mains. It runs the fuel bill up pretty high. Plus, it changes the price of the install because you're going to go from a boiler that's one size to a boiler that's a different size. And I say on here, don't accept no for an answer. Explain the fuel savings to the homeowner. Let them insulate them if they want. Maybe you can supply the insulation, but a lot of contractors don't want to insulate the pipes, but many homeowners would to get a smaller boiler and save the extra fuel. So give them the option, but it really needs to be insulated. Otherwise, the fuel bills are just way too high. Start from Peerless Boiler Company, the Series 63. We have 340 square feet of steam that we need to properly size the boiler with an insulated main. So if we're looking at 340 square feet of steam, we don't use the BTU column, we use the square feet of steam column. So which boiler do we need? If we find the proper number in the blue rectangle and slide to the left, it'll tell us what boiler to use. So we're looking at 340 square feet of steam. So that 383 would slide over to a 63-04L. That would be the proper size boiler. Now, what happens when we have the uninsulated main, and now we're at 515 square feet? You're probably getting ahead of me at this point, but you would slide down that column and find 515, and that would come out to 533 square feet of radiation. If you slide to the left, is an 05L. So it's actually 2 input sizes larger. So we have the 04L and then the 05 and the 05L. So we'll be paying for a lot higher input. And that input would go from, let me look at this, 147,000 to 206,000. So that's a pretty good jump in BTU. That's money you're buying, the fuel you're buying to put into the boiler that you're just wasting, because it's going to short cycle the boiler, drop the efficiency, and be less efficient. So proper sizing, insulate the mains, very important. So 2 points we're going to bring up, and then we're going to be done. An undersized boiler. When you have an undersized boiler, it does not fill all the piping and the radiation with steam. It's going to go to the radiators that are lowest pressure drop, and that doesn't mean they're the closest to the boiler. That could be a larger pipe, larger radiator somewhere, or that they don't heat from the boiler out. It depends on the amount of resistance for the steam to encounter as it goes to certain radiation. So it's always the least path of least resistance first. And then it may work on milder days. They put it in, you turn it on in the fall, and now it works. But when it starts getting colder out, at some point, it's not going to heat the house. Excessive fuel bills. The boiler is going to run when it gets cold nonstop, and you're not going to have enough heat. There's a line there that says, I want my boiler to run a long time, but I don't want a cast iron boiler to run all the time and not produce heat. That's the key. It has to produce enough heat to heat the structure. So it should cycle off, especially cast iron boiler, should cycle off occasionally, but we don't want to run all the time and not heat the building. Point we're going to bring up is oversized boilers. Oversized boilers are going to have an erratic operation. They're going to short cycle too much and just creating the steam way too fast. As you increase the velocity of the steam because of the size of the pipes, then you slow down the rate. It's going to condense faster. It's going to be a lot of issues. And you're going to short cycle the boiler. The shorter the cycle on that boiler or burner is going to drop the efficiency. And it could cause, on an oil boiler, it could cause some sooting also, some light sooting, which acts like an insulator. So you don't want to have soot in your product. Could be a noisy system. You could get some water hammer due to a lot of condensate up there from short cycling. You could end up with water leaking out of some of the vents because it can't get back to the boiler fast enough because we're making too much. There's just a couple of things there. Of course, increased fuel consumption. Anytime you oversize a boiler, it doesn't matter if it's hot water or steam, you're going to raise your fuel bill. It can produce higher maintenance or repair costs. So it's going to cost you more money in the life cycle of that boiler, not only in fuel, but in maintenance and service. Thanks for sitting through this with us. If you have any questions, contact us via email, text, phone, whatever. And visit us at comfort-calc.com. You'll see it in the lower right-hand corner. And if you have any, if you want to support us to help pay for the site, and the name of the site. There is a way on our homepage to do that that has no out-of-pocket cash. Just look at that. Thanks.